All right, so why is hydrogen located on the left side of the periodic table with the active metals, even though it's a gas? Hydrogen's location is related to its electron configuration, not its properties. Hydrogen can be used as a fuel for automobiles because it's flammable. So there's water cars where they take water and they separate the hydrogen from the oxygen. And as you will learn soon, that when something's on fire, it combines with oxygen. So they separate the water to have hydrogen and oxygen. Then they burn the hydrogen with oxygen, and guess what the product left over is? Water. It's pretty perfect. Anyways, why do the elements in a group have similar properties? Elements in a group have similar properties because they have the same number of valence electrons. Valence electron is an electron that is the highest occupied energy level of an atom. So when the A groups in the periodic table are numbered 1 through 8, the group number matches the number of valence electrons in the electron configuration of an element in that group. Valence electrons play a key role in chemical reactions. Properties vary across a period because the number of valence electrons increases from left to right. Elements in a group have similar properties because they have the same number of valence electrons. The properties are not identical because the valence electrons are different energy levels. So the more electrons they have, the more energy levels they have, but the valence electrons are the ones on the highest level, the outer ring, if you think about the Bohr model. Because hydrogen has a single valence electron, it is grouped in the elements such as lithium and all those other ones, lithium, sodium, potassium, because all of them have one valence electron. What are some properties of A groups in the periodic table? Well, the elements in 1A are called alkali metals. These metals have a single valence electron and are extremely reactive. Because they're so reactive, alkali metals are found in nature only in compounds. In other words, they don't float about by themselves. Okay? The reactivity of alkali metals increases from the top of group A down to the bottom. And that's because of how many electrons they have, how many protons. Sodium acts violently in water and releases enough energy to ignite hydrogen gas that is produced. In the chemical reaction, it separates the hydrogen from the water, and then the hydrogen catches on fire. When you put just sodium, okay, just sodium. So sodium and potassium are stored under oil and kept to keep them from reacting with oxygen and water vapor. So even moisture in the air can have an effect on sodium. Cesium is so reactive that it's usually stored and sealed in a glass tube containing argon gas. So that can't even be around oxygen. Alkali metals, unlike most metals, alkali metals, and there's the listing of group 1A, are so soft you can cut with a knife. When sodium reacts with water, enough energy is released to ignite the hydrogen that is produced. So it's a thing. So B is showing what happens when you put a drop of water on sodium. So to the left is sodium, and then when you put water on it, that's what happens. Group 2A are called alkaline earth metals, and alkaline earth metals have 2 valence electrons. Metals in group 2A are harder than the metals in 1A. The melting point for magnesium is 650 degrees Celsius. That's pretty high, which is much higher than the melting point for sodium. Excuse me. Differences in reactivity among the alkaline earth metals are shown by the ways they react with water. So calcium, barium, they react with cold water. Magnesium will only react with hot water. But not with cold water. The thermal energy is kind of acting as a catalyst, so it needs a little energy in that case. No reaction will occurs when beryllium is added to water. So magnesium plays a key role in photosynthesis. The compound at the center of this process is chlorophyll. At the center of chlorophyll is the magnesium atom. So if you look at the molecular structure of chlorophyll, magnesium is an important part of that. The mixture of magnesium and other metals can be used as strong as steel but much lighter. The frames of bicycles and backpacks usually have some sort of magnesium in them. So when they talk about an alloy, they take one metal and then maybe they mix it in with a little magnesium to strengthen it. Calcium carbonate is a compound of calcium and carbon and oxygen is the main ingredient in chalk, limestone, and coral. Your toothpaste may contain a compound calcium carbonate because this hard substance can polish your teeth. Magnesium and calcium have essential biological functions. They provide materials used in construction and transportation. Your body also naturally, there's some people that can have a magnesium deficiency and they take supplements for that. Anyways, chlorophyll molecules in spinach contain magnesium. The oyster shell and a pearl are both made from calcium carbonate. The plaster cast that you get on your leg or whatever, that's calcium sulfate. So here is all the group 2A elements, and they're saying, look, magnesium and calcium are used a lot for different things and found in nature. Group 3A is the metalloid is starting to move over towards the other side of the periodic table, and it's called the metalloid and borons, the first one in the group. And it's three less familiar metals: gallium, indium, and thallium. All these have 3 valence electrons. That's why they're in group 3. Aluminum is the most abundant metal in Earth's crust. Okay. Now, we had a question on the last thing where it said, what's the most abundant element? That's oxygen. But when we talk about metal, aluminum is the most abundant metal. Aluminum is less reactive than sodium and magnesium. Aluminum is strong, lightweight, malleable, and it does conduct electricity and current. Maybe not as good as copper, but it certainly does conduct it. So here's the boron group, as it's sometimes referred to, or as the boron family. This is just the group 3A. All of these elements have 3 valence electrons. That's why it's called 3A. The compound boron, silicon, and oxygen is used to make glass that does not shatter easily when the temperature changes rapidly. Glass that contains boron is used to make laboratory glass and cookware. It's also, if I remember correctly, we use boron in photocells. So boron, silicon, and stuff. Anyways, we'll talk about that when we get to our laboratory on solar cells. But anyways, adding these things to certain chemical compositions make things stronger or better. Group 4A is the carbon group, non-metal, of course. 2 metalloids, silicon and germanium. 2 metals, tin and lead. Each of these elements has 4 valence electrons. Notice that the metallic nature of these elements increases from the top to the bottom of the group. Germanium is a better conductor of electricity than, say, silicon. Except for water, most of the compounds in your body contain carbon. We're carbon-based creatures. That's why you always hear people talk about carbon-based life forms on Earth and stuff like that. Or organic is another word that they use a lot. Here's all the carbons. Group 4A, basically silicon is the second most abundant element in Earth's crust. The clay used to produce this pottery contains silicon, and compounds are called, anything that contains silicon is called silicons. Okay. By the way, a lot of this stuff is used in electrical things, especially silicon and lead. Is a little bit hazardous for human beings, but it has its properties. The nitrogen family, group 5A, 2 nonmetals, nitrogen and phosphorus, 2 metalloids, arsenic and, I'm really bad at pronouncing these, whatever that word is, and 1 metal, whatever that word is. 5A contains elements with wide range of physical properties. Nitrogen is a nonmetal gas. Phosphorus is a solid nonmetal. But they all have 5 valence electrons. So when air is cooled, the oxygen condenses before the nitrogen because nitrogen has a lower boiling point than oxygen. Much of the nitrogen obtained from air is used to produce fertilizers. Nitrogen is very critical in farming. So if you look at these things, basically bags of fertilizer have tons of nitrogen in them. They also have phosphorus and potassium. Okay. Group 6, the oxygen family. Oxygen, sulfur, selenium. Here's the oxygen family. Sulfur is what they put in matchsticks. That's what gives it that smell. That's one of the first elements to be discovered and is found in large natural deposits. It catches on fire quickly. It's a good fire starter. Halogens is group 7A. Halogens have 7 valence electrons. Here's the list of them: fluorine, chlorine, bromine, iodine, and so on and so forth. And those could be used for a variety of reasons. Despite their physical differences, halogens have similar chemical properties. If you think of a halogen lamp, it's got one of those chemicals in it. So this is a photograph that shows how chlorine reacts with steel wool, just regular chlorine gas. The elements in group 8A are called noble gases. Now that's helium, neon, argon, krypton, xenon, and radon. All of those have 8 valence electrons, and they create different colors. You've heard of neon lights. They interact specifically with certain things. Why do elements in a group have similar chemical properties? What do you guys think? A, B, C, or D? Let's say they have the same number of valence electrons. Group 1 has 1 valence electron, group 2 has 2, group 8 has 8, so on and so forth. Group 2A, what would you expect to react most readily with water? Radium. In general, the metallic characteristics of A group elements with the period decreases from left to right. True or false? True. And that's it. That's all we got. Look at that, right before the bell rings. Couldn't have timed it better myself. Thank you.